Welcome to Chapter 8, all about recursion. Recursion is when a function calls itself to solve a smaller version of the same problem. Every recursive function needs two parts, a base case that stops and a recursive case that calls again. We will meet the call stack, trace factorial and recursive binary search, and then turn recursion into a plain loop using our own stack. Let's start with a simple question. Why do we need recursion at all? In this first part, we look at a task that a plain loop cannot handle. By the end of this chapter, you will be able to do four things. First, you will spot a broken base case. That means you can tell a missing or unreachable base case from a correct one. Second, you will trace values up the stack. You can follow a returned value through every frame as the calls finish. Third, you will read an activation record. You can name a call's parameters, its local variables, and its return address. Fourth, you will convert recursion to iteration. You can rebuild a recursive function using your own explicit stack. One idea matters most in this chapter. A recursive call is not special. It is just one more frame on the same call stack you saw with functions in Chapter 6. Each frame has its own parameters, its own local variables, and its own place to continue. Let's look at a real task. Numbers come in groups, and a group can hold more groups. The first line shows the data, a list with numbers and smaller groups of numbers inside it. We want to add every number, no matter how deep it sits. For this data, the total is 21. A flat list is easy. A flat list has no groups inside. You just write one loop and add each number. But this list is different. It has a group inside a group inside a group, and the next set of data may nest even deeper. Let's try to sum this nested list with ordinary loops. One loop reaches the top level. A group inside needs a loop inside that loop. A group inside that one needs yet another loop inside it. So you must fix the number of nested loops in advance, but you do not know the nesting depth until you look at the data. No fixed set of nested loops works when the nesting can go any depth. The loop variables cannot remember one thing: where was I in each half-finished group? This problem is real, not a trick. A fixed set of nested loops handles only as many levels as you wrote. Nested data can go deeper than any count you fix in advance. You can still loop over any depth, but only by keeping your own explicit stack of where I paused. That is the exact tool this chapter builds later. The task is self-similar. Summing a group is the same job as summing the whole thing, so we let a function call itself on each smaller piece. That is recursion, a function that calls itself on a smaller instance of the same problem. To sum a group, add each item. If an item is itself a group, sum it the same way. A base case stops the descent. A plain number just returns itself. Now the shape of the code matches the shape of the data. Nested calls for nested data. The loop failed because nested data needs an unknown amount of where was I memory. Recursion gives you that. Each unfinished call remembers its own spot, and the computer stacks those half-finished calls for you. This chapter looks inside that stack. A Russian nesting doll opens one way. To reach the smallest doll, you open every doll around it in order. This is the biggest one, doll 3. You open doll 3, and inside you find doll 2. That is one step deeper, just like a function calling itself on a smaller problem. You open doll 2, and inside you find doll 1, deeper again. Doll 1 does not open. That is where the opening stops. Doll 1 is the base case. Now you close them again on the way back out. First you close doll 1 back into doll 2. Then you close doll 2 back into doll 3. The closing on the way out is just like a function returning its answer. Let us name the shape we just saw. Many tasks work like this. To do n, you first do n minus 1, and then you use that result. The doll that does not open is the base case. It answers on its own, and it starts no new work. Every other doll is the recursive case. It does a smaller version of the same job, and then it uses the answer that comes back. Now where the doll picture breaks down. A real doll set has a fixed number of dolls. You can see them and count them before you start. But the depth of a recursive call is often unknown until it runs, as the nested list just showed us. Some tasks are naturally self-similar. The same steps work on a smaller version of the same problem. Look at factorial. N factorial equals n times n minus 1 factorial. So factorial of n needs factorial of n minus 1. A loop can multiply a running total, but nothing in the loop shows that n depends on a smaller copy of itself. Worse, some self-similar problems have no obvious loop at all. Searching a nested list or walking a tree are like this. The smaller problem is not a fixed number of steps away. Recursion lets the code look like the problem. To solve size n minus 1, then combine. That clarity has a cost. A hidden stack of pending work must live somewhere. Now we look at where.